Day 60 Notes, Advanced Algebra 2. Today we continue our discussion identifying types of polynomials by degree and by their graphs. Today we're going to look at these 5 different types of polynomials, and we'll talk about using special names or specific names for these types of polynomials. Once we get beyond this last option, however, we stop referring to polynomials by a special name and we refer to them just by their degree. For example, anything beyond a power of 4 would be called, say, a 5th degree polynomial, or bigger than that, a 6th degree, or 7th degree, or 8th degree polynomial. Let's start back at the beginning, however, and look at this first polynomial. In this case, what we would call a constant, well, this is a polynomial that has no x values. Now, we could imagine that there's an x to the power of 0 written here, a sub 0 times x to the power of 0. Well, x to the power of 0 is just 1, so really, we can imagine that that's not even there. A sub 0, as we discussed on Monday, is simply a number. So a constant polynomial is simply a number. A linear polynomial is a polynomial that follows this form. We have a sub 1, so a number in place of that, in front of our x value, our variable, plus a sub 0, a constant. Now, you may have seen the form mx plus b before, and that's very similar. Essentially, it's the same type of polynomial, where m represents the slope of a straight line, and b represents the y-intercept. That's the same result that we get here when we're talking about a linear function, or a linear polynomial. A sub 1 is the coefficient in front of x. A sub 0 is the constant. This is an example of what we would call a linear function. Now, quadratic functions are something that we practiced several times over the last few weeks. A quadratic function or quadratic polynomial follows this form, where we have a coefficient times x squared, plus another coefficient times x, plus our final coefficient or constant at the end of the expression. Constant x squared plus a constant times x plus another constant is the form of a quadratic expression or quadratic polynomial. A cubic polynomial is next. This time we have all of the features of a quadratic polynomial. We just add to it a term that has a power of 3. And lastly, a quartic polynomial has the same features of a quadratic, along with the features of a cubic polynomial. And lastly, we add to it a final term. This time, the power is raised to the 4th. Again, we're going to get used to using these 5 vocabulary words to describe the types of polynomials that we see. This would be describing the types of polynomial by degree. So let's take a look at these for practice. In order to name a polynomial by degree, we must pick the largest degree of the polynomial. It would be nice to have these examples written in standard form first. So let's check that. Option A is already in standard form. We have the largest degree listed first, and they decrease as we move down the line, as we move through the rest of the terms. Option B is a single term, so it's already in standard form. It can't be out of order. Same thing with option C. That's not out of order at all. It's just a single number or a constant. Option D, however, needs to be reorganized a little bit, and I would say that this is f of x equals negative 4x cubed plus 2x. We write it this way so that the function's now in standard form. For option E, ignore that little extra mark there. That should just be f of x. Let's call this f of x equals 5x to the fourth plus 2x squared minus 20. Now that's in standard form. And option F is already in standard form. It's in decreasing order. So what type of polynomials do we have here? Option A, what type of polynomial do we have? Is it a constant, a linear polynomial, a quadratic, a cubic, or a quartic? Well, you should recognize by the leading not the leading coefficient, but the leading term and its exponent, which is known as the degree of 2 matches with the quadratic polynomial. So this is a quadratic. Looks very similar to the problems we worked with last week. For option B, we have an exponent value of 1. Even though it's not written, we assume that it's there. And to have an exponent of 1 would be this type of polynomial here. This is a linear polynomial. Option C has no x value. It has no variable with it. So any number without a variable is what we would call a constant. And option D has an exponent value of 3, a cubic polynomial. Option E has a fourth power that's in its leading term. So this is an example of a quartic polynomial. And option F also has an exponent of 1, just like option B. So we would say that that is a linear polynomial. It'll be up to you to memorize these 5 types of polynomials and to be able to recognize those types of polynomials by their degree. Now let's take a look at how each of these polynomials look when we graph them. We'll do some examples of each. A constant, linear, quadratic, cubic, and quartic polynomial graphs. And I bet you'll be able to tell what some of these are going to look like before we put them into a calculator. I'm going to pause the recording now and create each of these graphs using the TI Inspire, and I will copy those into this notebook. And I'll ask that you sketch them into your notebook as well. And here we go with the results. This first sketch here shows what a constant function will always look like. Constant function will always create a horizontal line. Now in this case the constant was equal to 5, so this horizontal line crosses the x-axis at 1, 2, 3, 4, 5. Sorry, the y-axis at 5, not x. So if I had f of x equal -2 as a constant, well, that would be a horizontal line through y equals -2. We have a horizontal line there. But a constant graph will always, a constant polynomial will always graph out to be a perfectly flat line. Now a linear function, in this case 3x minus 2, creates another straight line, only now we have a slope to this. That slope value of 3 indicates the rise and run, so we would go up 3 over 1, up 3 and over 1, up 3 and over 1, or down 3 and left 2, and so on and so forth. We can recreate points on this line. But the slope and the intercept are points that we can graph. But when it comes to the polynomial, a linear function will always form a straight line. Then when we move on to a quadratic polynomial, I think we should recognize at this point that a quadratic polynomial is curved and it creates a single curve. This U shape is what we call a parabola. This is something that we talked about in last unit. A parabola always is a result of a quadratic expression or quadratic equation. As we start to get into the cubic graphs and the quartic graphs, you should start to recognize a pattern that's forming here. This is an example of a cubic graph that comes from one side and it increases, makes a bend and a second bend, and then it races off in the other direction. This too is a graph of a polynomial. We know that it is because this is continuous and smooth. But if you start to notice, these degrees start to have they start to give us an idea of how the shape of the graphs will be. We'll finish with this last sketch today. X to the fourth power plus 2x cubed minus x squared minus 2x plus 3 produces this shape. And again, this degree, this power of 4, should give you an indicator of how this graph will look. Can you see the pattern that's forming when I look at each of these degrees? And perhaps even this one here. There's a little bit of a giveaway. But more specifically, these last three here. Take a look at each of the graphs. Compare them to the degrees of the graph and see if you can determine what the relationship between the degree and the shape of the graph is. We'll continue with this discussion tomorrow.